See these lines? They aren't decoration. Engineers actually force concrete to crack here on purpose. It's called a control joint, and without this planned failure, the whole slab would shatter. Here is the genius engineering behind why concrete is designed to break. We tend to think of concrete as permanent. It is the material we choose when we want to build something that lasts forever. From massive dams to the foundations of skyscrapers, we treat it as artificial rock, heavy, solid, and immovable. Because of that reputation, seeing a crack in a concrete wall or a basement floor feels like a sign of structural failure. It looks like a mistake. Our intuition tells us that if the material were truly strong, the surface would remain unbroken. But in the world of civil engineering, a crack is not always a defect. In fact, many structures are designed with the assumption that they will crack and that the building will stand safely regardless.
To understand this, we have to look at the mechanical personality of the material. Concrete has incredible compressive strength. You can pile immense loads on top of it, squeezing the atoms together, and it will hold up without issue. This is why it works so well for columns and footings. However, it has a significant weakness: tension. When you apply a pulling force or try to bend a concrete beam, it struggles. Its ability to resist being pulled apart is only about 10% of its ability to resist being crushed. This makes concrete a brittle material. Unlike steel or rubber, which are ductile and can stretch significantly before they snap, concrete is stubborn. It does not stretch well. When tensile forces are applied, it doesn't deform to accommodate them. It simply reaches a limit and separates. Engineers measure this in terms of strain, the amount of material deforms under load. Concrete has a very low strain capacity. Once that microscopic limit is exceeded, the internal bonds break. The problem is that tensile stress doesn't just come from heavy weights, it often comes from the concrete itself. When concrete is first poured, it is a wet plastic mixture of water, cement, and aggregate. As the cement hydrates and hardens, it consumes some of that water in a chemical reaction, while the rest evaporates into the air. As the water leaves, the volume of the concrete physically shrinks. It wants to occupy less space than it did when it was wet, but in reality it is cast against the ground or connected to other rigid structures. This creates restraint. Friction with the ground holds the bottom of the slab in place while the top tries to shrink. This tug-of-war generates massive internal tension. Eventually, the force of the shrinkage overcomes the tensile strength of the concrete, and it tears itself open to relieve the pressure. This is known as drying shrinkage. Temperature swings add another layer of complexity. Concrete expands on hot days and contracts on cold nights. This thermal cycling forces the material to move. Since it is rigid and brittle, it often cracks rather than flexing to accommodate these daily changes in volume. Since engineers cannot change the laws of physics, they don't try to stop every single crack. Instead, they design systems to manage them. The most common solution is reinforcement. We embed steel bars or rebar inside the concrete to create a composite material. Steel is excellent at handling tension. When the concrete inevitably cracks, the steel takes over, acting as a bridge across the gap. It holds the two pieces tightly together, preventing the crack from widening and maintaining the structural integrity of the element. We also use geometry to our advantage. If you look at a sidewalk, you'll see lines scored into the surface every few feet. These are control joints. We are intentionally weakening the slab in a straight line. By doing this, we are inviting the concrete to crack there rather than randomly across the center of the panel. We're not preventing the physics of shrinkage, we're just organizing the visual result to look tidy and intentional. Prevention strategies also include curing. By keeping new concrete wet or covered with blankets, builders slow down the drying process. This allows the concrete to gain strength before the shrinkage stress becomes too high. Ultimately, the presence of a hairline crack does not mean the structure is unsafe.
It is simply the visual evidence of a rigid material adjusting to the reality of volume changes. Good engineering distinguishes between structural failure and serviceability. We design concrete to perform its job for decades, even if the surface isn't perfectly pristine. The goal is durability and safety, not cosmetic perfection. So the next time you see a jagged line in a driveway, remember that it isn't necessarily a mistake. It is just the concrete relieving its stress, so the structure doesn't have to. So those cracks aren't failures. They're actually proof the steel reinforcement is engaged and holding everything together. If you want to crack the code on more engineering mysteries, hit that subscribe button.